Good morning. Today is November the 20th. This is Math 1314. So I just want to go through a few things here as we get started and get into the last couple of weeks of the semester. First of all, let me remind you that WebAssign homework is due tomorrow, November the 21st. You have a couple of sections of WebAssign due. Also remember that the Exam 3 review is up. Exam 3 covers the sections that I've got listed here, 3.4, 3.7, on combining functions, inverses, composition. Covers sections 6.1 and 6.2 on exponential equations, including compound interest. Remember, those are formulas that I will supply to you. 6.3, 6.4, and 6.5 are all properties of logarithms. And then section 6.6 on exponential equations and logarithm equations. So that Exam 3 review is up on my Google site. Please be working on that over the Thanksgiving holidays, if at all possible, to start getting yourself ready for Exam 3. The Exam 3 window opens next Thursday, November the 30th. So that's a week from Thanksgiving. It goes from November the 30th through Tuesday, December the 5th. I have online office hours this week, tonight, and tomorrow night from 8 to 9 p.m. Don't hesitate to come by if you have questions. I will be on campus next week, November the 29th and the 30th. I'll go ahead and post times on those when I send out my weekly update later this week, towards the end of Thanksgiving. But I will be on campus those 2 days. One other thing I want to point out is, and I'll mention this at the end of this lecture also, is I will be answering email and WebAssign messages over the Thanksgiving holiday. So if you have any questions over the holiday and you really got to get it answered, or you need to get something straightened out, please email me or send me a message through WebAssign. I'll be happy to help you out. It may take me a little bit longer to respond over the Thanksgiving holiday, but I'll still respond over the week, definitely. Also, I have online office hours on Sunday of this coming week from 7:30 to 9 o'clock. I didn't list that here, but make sure that you also know that you've got Sunday hours as well. So let me actually write that in here. Sunday, 7:30 to 9 p.m. Okay, so today we start kind of our last topic of the semester. So this is rapidly coming to a close, and we want to talk about systems of equations. We're going to start talking about systems of equations today, and we will cover that again next Monday. Try to finish most of what we want to do next Monday. And if there's anything left to finish up, we'll finish it up the following Wednesday on video. Or I'll post a video sometime in between, possibly, depending on how long that video takes. So we want to start talking about systems of equations. And you should have covered systems somewhere before, but we're going to do a little bit of reviewing, and then we're going to do some stuff that's definitely things that you probably haven't seen before. Systems of equations. Now today what we're going to do is we're going to look at two equations and two unknowns. Or two variables. Next week, when we turn our attention to matrices and using matrices to solve systems, we'll look at three equations and three unknowns. All right, and with two equations and two unknowns, we're going to look at linear systems and nonlinear systems. When we go on to three equations and three unknowns, we'll only look at linear systems. So first of all, a linear system, two equations and two unknowns. So linear systems, two equations in two unknowns, sometimes called a 2-by-2 system. Okay, and there's actually two methods for solving these kinds of equations as well, so, or these kinds of systems. So let's look at this system. We have x plus 3y equals 5 and 2x plus 3y equals 4. And so we're going to solve this system. So we're going to solve this system using a method called substitution. First of all, let's talk about graphically what's going on here. Remember that these are both linear equations. So x plus 3y equals 5, its graph is a line. And 2x plus 3y equals 4, its graph is a line, right? When you're talking about linear systems, 2 by 2 linear systems, you're talking about two lines. You're talking about where do these lines intersect. Don't forget graphically that that's what you're doing here, is you're asking this question: where do these lines intersect? And certainly one way you could do this is you could go ahead and graph the system and see if you could figure out where they intersect based on the graphs. Now by hand, this is not necessarily the best method in the world, because if you do this by hand, it may be that it's hard to be accurate enough. And even with a graphing calculator, it still may be hard to be accurate enough to get a really good solution. And so, a graphing calculator certainly have apps built into them to solve the system for you, but the process would be completely hidden behind the scenes, and you'd have no idea what the process was that was being used. Okay, so x plus 3y equals 5. The x-intercept for this graph, remember you substitute 0 in for y there, is 5, and the y-intercept, when you substitute 0 in for x, is going to be 5/3. And so this graph crosses at 5, 0, and it crosses at 0, 5/3. And see, right there, you're just estimating that point as best you can. And so right away, we're going to lose a little bit of accuracy when we graph this one. All right, so when we graph it, I'm going to try to be careful to draw at least a moderately good straight line here. Like there, okay? All right, and then the other line, you have 2x plus 3y equals 4. The x-intercept on that graph, when y is 0, you get x to be 2. And the y-intercept, when x is 0, you get 4/3. All right, so you get 1 1/3 and 2. Like so, and so you get those 2 points right there. I'm going to graph this one in a different color right here. And so we get this graph right here. Now you can see, pretty clearly that it's difficult to graph these by hand and come up with a good solution. But the point of intersection, that's the whole premise graphically here. The point of intersection is the solution to the system. And this one, it kind of looks like I've got -1, 2 as the point here. Right, it vaguely got the two graphs intersected around -1, 2. So what I'm going to write right here, it looks like -1, 2 might be the solution. To the system. And so what could we do? We could check that. So we could check -1, 2, and we could see if that makes both equations true. So you have x plus 3y equals 5. So that'd be -1 plus 3 times 2 equals 5. And sure enough, that's true. 5 equals 5. So -1, 2 makes the first equation true. And then the second equation is 2x plus 3y equals 4. And so if we checked, we put -1 in place of x, and we put in 2 in place of y. And sure enough, we get -2 plus 6 equals 4, and we get 4 equals 4. So that one checks also. So the -1, 2 is the point of intersection of these two. And we can kind of sort of get that point based on our graphs, but we had to be really very careful to do this. So what we want to do is look at algebraic methods. So we're going to talk some about the graphical ideas behind some of these systems, especially when we talk about nonlinear systems. But what we're going to do is focus on the algebraic methods for solving these systems of equations. Okay, so let's get back to our system then. X plus 3y equals 5, 2x plus 3y equals 4. And so we know that negative 1, 2 is the solution to this system. So let's find this algebraically by using substitution. And that's what I'm doing here, is going back and reviewing that method. You should have seen that method somewhere before in an algebra class. So with substitution, the first step is to solve one equation for either variable. Okay, so what that means is, so for example, in this problem, if I took, I'm going to do this in a different color so you can separate it from the problem. If I took my first equation, x plus 3y equals 5, and I solved this equation for x, which would be easy enough to do, all I have to do is subtract 3y from both sides, and boom, I've got this equation solved for x, right? It's x equals negative 3y plus 5. So there's my first step. I solved the first equation for one of the variables. I solved it for x. The second step is to substitute this expression into the other equation. Okay, so that's what we're going to do. We're going to take the other equation, we're going to write it down again, try to keep things straight as best we can. So here's my other equation, is 2x plus 3y equals 4. And what I'm going to do is I'm going to substitute this expression in place of x. Okay, so when I do that, I have 2 times, and I'm going to put this in red right here. In place of x, I'm substituting negative 3y plus 5, like that. And then you have plus 3y equals 4. And what you notice is when you make this substitution, this equation, the resulting equation, only has one variable. That's what you're trying to get, is just an equation that has one variable. And sure enough, that's what all this one has. So now you solve for y. So now solve for the remaining variable. Okay, so when we solve for the remaining variable, in this case we're solving for y. Easy enough, it's a linear equation. So you have negative 6y plus 10 plus 3y equals 4. Collect like terms, you get negative 3y plus 10 equals 4. Subtract 10 and you get negative 3y equals negative 6. Divide by negative 3, boom, we get y equals 2, and we've got one of the variables. And then finally, we use this solution. Use this solution to solve for the second variable. And so we've got y equals 2, and then we take either equation, doesn't matter which one, by the way, and so I'll take x plus 3y equals 5. And you substitute y equals 2 in there. So you have x plus 3 times 2, like that, equals 5. Easy enough. You get x plus 6 equals 5, x equals negative 1. And we've got the solution to the system, right? We know that y equals 2 and x has to be negative 1 is our solution. We saw that graphically on the previous page. And so we've solved this system. All right. So this was the substitution method, remember, for solving the system. Okay, for solving a linear system. Now the next method that I want to review here, so let's look at a different system. So let's say I have this system right here. You have negative 2x plus 5y equals negative 42, and 7x plus 2y equals 30. And this time we want to solve by what we call the elimination method. Sometimes you'll see this referred to as the addition method. So we've solved by substitution, and now we want to solve by elimination. All right, this is the other algebraic method. This method actually more directly ties into solving systems by matrices. Now with the elimination method, what you're trying to do is you're trying to add the equations together. So add, we put that in quotes, add the equations together so one variable is eliminated. Okay, so now look at this system right here. Notice how everything's lined up really nicely, right? X's are lined up, Y's are lined up, constants are lined up. All right, so line everything up, just like this system right here. So line all terms up. And probably all like terms up is what I should say right here. And this system is already like this. And when you add these two equations together, and I'm literally going to add them like this, notice I just get 5x plus 7y equals negative 12. Neither variable was eliminated. So we have to fix this system so that when I add them together, one of the variables is eliminated. So neither was eliminated. Fix, I'm going to put quotes around that, the system, so one variable is eliminated. All right, so how do we do that? And again, this is something that should bring back old fond memories for you. You should have done this somewhere before in an algebra class. I'm kind of assuming that you've done this. That's why we're just presenting this as a review. So first of all, you pick the variable you're trying to eliminate. So in this problem, let me eliminate y. Okay, so let's eliminate y. So to eliminate the y, what you need to do is you need the coefficients of the y's need to be opposites. So coefficients of y's need to be opposites. So how do I do that? Well, if I take the first equation and I multiply the first equation by 5, I'm sorry, not by 5. It'd be good if I chose the right number here. If I multiplied the first equation by 2, so notice now the coefficient of the y is going to be a 10 when I do that. And I multiply the second equation by 5. Notice the coefficient of the y here is also going to be a 10. Now I need them to be opposites, so I make one of them negative, and it doesn't matter which one. So when I multiply the first equation, every term by 2, in the second equation, I multiply every term by negative 5. Let's see what this system looks like now. So you have negative 4x plus 10y equals negative 84, and negative 35x minus 10y equals negative 150. Okay, so let's see what happens here. Now I add the two equations together, and I accomplished what I was trying to do. The y's drop out, notice. Now you get some big numbers here, so let's see how this works out. You have negative 39x equals negative 234. Okay, and sure enough, when we divide both sides by negative 39, we can solve for x here, and we get x to be equal to 6. Negative 234 divided by negative 39 is exactly equal to 6. So that was nice. So we've got our first variable. First variable is 6. Now find y. And to find y, choose either of the original two equations. So let's say I take negative 2x plus 5y equals negative 42. And I'll take x equals 6, and I'll substitute in place of x there. So let's see. So this would be negative 2 times 6. I'm going to go ahead and put that in a different color because I'm substituting. plus 5y equals negative 42. So you get negative 12 plus 5y equals negative 42. Add 12, you get 5y is equal to negative 30. And then divide by 5, and you get y equals negative 6. And so there's our y coordinate for our solution. So the solution to the system, we could check it certainly. So the solution to the system is 6, negative 6. If I graph both of those lines up there at the very top, I would see that they crossed at the point 6, negative 6. I could certainly check both of those. Never a bad idea to check these and make sure that they actually make both equations true. And I could quickly do that. I have negative 2 times x plus 5 times y equals negative 42. There's the first equation. The second equation is 7 times x plus 2 times y equals 30. And I'm substituting 6, negative 6 in there. I'm going to put that in red. Right, and you can do the arithmetic here. First equation is negative 12 plus negative 30 is negative 42. Check. That makes that true. Second equation, 42 plus negative 12 is 30. Check. This negative 6, negative 6 is definitely the solution to that system. Yay, so we've got the right solution here. And remember, that's the place where those two graphs would intersect each other. Those two lines would intersect each other. Okay, so going back over these last two screens, go back the other way here. We just use the substitution method here, where we solve one equation for a variable and substitute it into the other equation. And then we've used the elimination method here. And then actually we used the graphing method in the very first screen right here. And we saw that that was maybe not the best method because it's difficult to get a solution that's accurate enough, depending on the solution and depending on what kind of technology you're using and everything. Okay, so we've gone through a quick rundown of linear systems. Now also remember that with linear systems, I should look at the graphical situation one more time, that when you have two graphs like this that intersect, right, then the point of intersection is the solution to the system. Boom. And so a system like this has one solution. System has one solution. Sometimes called an independent system. Okay. Since you're talking about looking at where two lines intersect, though, another possibility could be that the two lines actually are parallel, that they never intersect. Right? And so in this case, the solution has no system. It'd be nice if I said that correctly here. The system, there you go, system has no solution. This is sometimes called an inconsistent system. And then finally, one last possibility graphically with a linear system of two equations and two unknowns is that the two lines end up being actually the same line. When you graph them, one line actually lies on top of the other line like this. And so in this case, there's an infinite number of solutions, so infinitely many solutions, because they intersect in an infinite number of places. And this is sometimes called a dependent system when this happens. All right, with inconsistent systems and dependent systems, remember that what happens algebraically is that in an inconsistent system, you end up with an equation that makes no sense. So you end up with an equation like 0 equals 3, right? And you end up with an equation like that that's clearly false. And with a dependent system, what ends up happening is you end up with something like this, 0 equals 0. You end up with a obviously true equation. right? In other words, all the variables drop out and you end up with either a true or a false statement when you try to solve it algebraically. And that will come up a little bit when we talk about matrices again. Okay, so what our main goal today is to look at nonlinear systems. So nonlinear systems means that we are talking about a system of two equations and two unknowns where at least one of the equations is not aligned. Its graph is not aligned. At least one equation has a graph that is not a line. Now, we're not going to go crazy with this, but we are going to look at some second degree equations and how that's going to how that works out. Now, first of all, a little bit about graphs that we want to talk about. So let's do a little bit of reviewing with graphs here. So we know that if you have an equation like this, ax plus by equals c, that graph is a line. Okay, so that's a linear equation, right? Both variables are raised to the first power. But if you have one equation is squared, so for example, if the x is squared, but not the y, this is an example of a nonlinear equation. And if the x is squared but not the y, this graph is a parabola. And if the x is squared but not the y, then the parabola is either going to open up or the parabola is going to open down, depending on what the constants are that are in there. All right, if the y is squared but the x is not, still nonlinear, the graph is a parabola also, but now it's a parabola that opens either left or right, depending on the constants that are in the equation. Now, by the way, I'm not going to necessarily hold you responsible for identifying these shapes like this. We've talked about parabolas before, earlier in the semester, as functions. And so that's not really what we're talking about here. We're just talking about being able to go into a problem and graphically have some understanding of the graphical underpinnings of the problem that you're talking about. So you can kind of make some conjectures about how many solutions that you're going to get to the system. And so it would be nice to know going into a problem, hey, I know that this graph is a parabola. I know this graph is a line, right? All right. So if you have an equation like this, x squared plus y squared, now notice both variables are squared, but notice that the coefficients of the x squared and the y squared are 1s here. If you can write the equation as x squared plus y squared equals c, x squared plus y squared equals a constant, and if c is greater than 0, then this graph, in other words, c is positive, this graph is a circle, right? Centered at 0, 0. Centered at 0, 0. And we have not talked about circles at all, and it would be nice here. And so I'm going to spend about 4 minutes talking about some basic things with circles centered at the origin. So an equation like this, x squared plus y squared equals constant, is a graph that's a circle centered at 0, 0. And how do you get an idea of what the graph looks like? Well, what turns out happens, we could use the distance formula to prove this, but if you have an equation like that, so this would be a typical equation like that, x squared plus y squared equals 4. The radius is always the square root of this number, of this constant over here. So the radius of the circle is always the square root of that constant. So in other words, that constant is always the square of the radius. So in our problem here, this radius would be 2. And it's a very easy equation to graph. You know that the center is at 0, 0. Remember, we said on the previous screen that equations in this form always have a graph that's a circle centered at the origin. So this would be a circle centered at the origin with a radius of 2. like this. Right? Pretty easy to get the sketch the graph. If you have x squared plus y squared equals 10, then the radius of this circle would be the square root of 10, which is a little bit bigger than 3. It's like 3.16, yeah. I was going to say that, but then all of a sudden I started questioning it. So on a problem like this, or in a graph like this, then you would just estimate as best you can where 3.16 is. So a little bit bigger than 3, basically. Centered at the origin, and here would be my circle. Like so. Okay. If we had, let's say, 3x squared, get the constants looking better here. So 3x squared plus 3y squared equals 75. Then what happens? First of all, the equation is not exactly in the form x squared plus y squared equals constant, because I've got 3x squared plus 3y squared equals a constant. So what do? I go through and I divide everything by that constant of 3. And when I do that, sure enough, I end up with that equation, x squared plus y squared equals 25. And so that graph would be a circle with a radius of 5, right? Radius would be the square root of 25, which would be 5. And then I'm going to kind of change the scale here, and we are going to sketch this graph. And I'm going to kind of cheat to get it to fit on my screen here. Since its radius is 5, that point would have a coordinates 0, 5, and that point would have coordinates 5, 0. Like that. Right? And now, this is okay. As long as I label it correctly, I'm good. All right, a couple of other things about circles. If you have x squared plus y squared equals -9, if that constant is negative, there is no graph for this equation. This is not a circle, because there's no way you could get two perfect squares like that to add to give -9. Wouldn't be possible to do. And if we're talking about real numbers here, obviously. So there would be no graph in an equation like that. All right, so now notice that if you have an equation like this, let's say we have 2x squared plus 3y squared equals 9, that there's no way, because the coefficients of the x squared and the y squared are different. Notice that on the equation at the very bottom here, the coefficients of the x squared and the y squared were exactly the same. And so I could write this equation in the form x squared plus y squared equals a constant, because I could just divide everything by 3. There's no way to do that in this problem. So no way to write as x squared plus y squared equals a constant. And so this is not a circle. When those coefficients are different, like this one is, this graph is an ellipse. All right, so we're not going to get into anything big about ellipses, but this is an ellipse centered at 0, 0. And you could sketch a decent sketch of this ellipse by just plotting intercepts. If you plotted intercepts, you could get a decent graph. You could get a pretty good graph, actually, if it was centered at the origin. So the general moral to the story here is if you have the equation in the form x squared plus y squared equals a constant, that graph is a circle, right? If I can make it so that the coefficients of the squared terms are both 1s, then that graph is a circle centered at 0, 0. And the radius is the square root of c. And remember, c has to be positive. If the equation cannot be written like that, so you have both an x squared and a y squared, they're both positive coefficients, but they're different like this, then you have ax squared plus by squared equals c. And this graph is an ellipse centered at 0, 0, and plot intercepts in this case to make a decent sketch if you really wanted to do that. Remember, that's not really our main focus here. But it would be nice to know that the graph's an ellipse going into the problem. Okay, and then finally, you could get, so we've talked about circles and parabolas and ellipses. The final type of graph is if the equation is much like an ellipse, but it's a subtraction problem instead. So ax squared minus by squared equals c. So notice the only difference there is that this is a subtraction problem instead of an addition problem. Then this graph is a hyperbola. And we definitely don't want to, not going to get bogged down into graphing hyperbolas, but know that the hyperbola is either going to, first of all, it's centered at 0, 0, and the hyperbola is a shape like this. It's a graph that actually has two pieces to it. And so the hyperbola is either going to open left and right, or it's going to open up and down like that. And again, if you plotted intercepts, you could get an idea of which way it opened just based on the intercepts. And you could make a very vague, rough sketch of this to have some idea of what's going on. All right, so what do we have here? We have equations where you have only one squared term as a parabola, and then if you have two squared terms, you either are going to get a circle centered at 0, 0, an ellipse centered at 0, 0, or a hyperbola centered at 0, 0. Now, if we added x and y terms in there, notice these have just got x squares and y squares in them. If we add x and y terms to those equations, then we make it a little bit more complicated, and then we get circles, ellipses, and hyperbolas centered somewhere besides the origin, which is definitely not what we want to talk about in this section. All right, so let's look at systems. So that was a very, very fast rundown of the graphs there. Not absolutely essential that you know that, but it's always a good idea to have that in your mind as you start in on a nonlinear system. So look at solving nonlinear systems. That's what we want to do next. All right, so we are going to be tackling problems out of your textbook. This is in section 7.3 of your textbook. This is page 611, and we're going to start off with problem number 6. So number 6, we have x plus y equals 4, and x squared plus y squared equals 9. And you can see why this is a nonlinear system, because the second equation is not linear. And based on what we've just talked about, what do we know? That this graph is a line. In this graph, because it's in the form x squared plus y squared equals a positive constant, this is a circle centered at 0, 0. So if you think about the graphical underpinnings of this kind of problem, notice that you have a circle and a line. So one way that a circle and a line could intersect is they could intersect at 2 points. So you could get two solutions to the system. But that's not the only thing that could happen. You also could have a circle and the line ends up being tangent to the circle. And if the line ends up being tangent to the circle, in other words, it just touches it at one point, then you have one solution. And finally, what certainly could happen is that you have a circle and you have a line, but they don't intersect at all. Right? No intersection at all. So what happens here? We could have two solutions. In this picture, we could have one solution like this picture, or we could have 0 solutions like this picture. You could certainly graph this system to get a better idea of what's going to happen here with these two equations. All right? So what we're going to do is we're going to solve this using substitution. And we used substitution a few minutes ago to look at a linear system. So we're going to solve this using substitution, and we're going to see which one of those graphical pictures we have. And I'm see if I can spell the word substitution correctly. There you go. Solve using substitution. So what we're going to do is we're going to take one equation and solve for a variable. In this case, pick the linear equation if at all possible. Pick the linear equation to do this. So if I take the linear equation and x plus y equals 4 and I solve it for y, let's say, solve for y, then that means just subtracting x from both sides, and I have y equals negative x plus 4. And now remember what you do is you substitute into the other equation. Always the other equation. Never the equation that you started with. Okay, so I take my other equation, x squared plus y squared equals 9, but in place of y, right here, I substitute what I found y to be, and that was that y was negative x plus 4. And so now notice you've got an equation that involves only one variable. Only x's are in this problem now. And so now solve for x. Whoops, let me make this consistent here. So now solve for x. So I have x squared plus, and you've got to square out negative x plus 4. And remember, that's negative x plus 4 times negative x plus 4 if you have trouble with that. So when you multiply that out, you get x squared minus 8x plus 16, because you're going to get two negative 4x's in there. And that would equal 9. And so I've got a quadratic equation. I solve that quadratic. I get 2x squared minus 8x plus 16 equals 9. I just collected like terms there. And then subtract 9, and you get 2x squared minus 8x plus 7 equals 0. Like that equation right there. All right, and then I go ahead and solve that equation. It would be really nice if that was factorable, but that is not factorable. Yuck. So I picked a messy problem to start with. And so what do I have? So I'm going to put yuck here just to complain a little bit. So what do I have to do? I have to use the quadratic formula to solve this equation. Oh my gosh. So remember that the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. And so when I solve this equation, I get x equals the opposite of b, so that'd be 8 plus or minus the square root of b squared, which is 64, minus 4 times a times c, so this would be minus 4 times 2 times 16, all divided by 2 times 2. And so I get 8 plus or minus the square root of 64 minus, and this is 4 times 2. And I don't know, I substituted in wrong right in there, and I'm not really sure what I was doing right in there. So let me kind of correct that underneath that radical. Just would look back and I noticed that this was not right. So it's b squared, which is 64, minus 4 times a, which is 2, times c, which is 7. That's better. And so that would give you minus 56 right here, all over 4. And so you get 8 plus or minus the square root of 8 over 4, or 8 plus or minus 2 square root of 2 over 4. Or if you could finally simplify there, and you get 4 plus or minus the square root of 2 over 2. And so I get two x values as solutions. And notice there's no way you'd ever find these graphically. But you get 4 plus or minus the square root of 2 over 2 here. You can look for decimal approximations on these and make sure that they kind of, agree with the graph. And we are going to look at the graph of this in a second. All right, so you certainly could kind of get some quick decimal approximations. So 4 plus the square root of 2 over 2 would be about 5.4 over 2. So it's approximate at that point. And so that's approximately 2.7. Square root of 2 is about 1.4. And then you have 4 minus the square root of 2 over 2. So it'd be 4 minus 1.4, or about 2.6 over 2, or about 1.3. So those appear to be the solutions, the x values for the solutions, about 2.7 and about 1.3. To find y, we take our equation that we've solved for y equals negative x plus 4, and we find y this way. And I really wasn't planning on the problem going on this long, and so I kind of didn't leave myself a lot of space here. So you have y equals the opposite of x, so this is the opposite of 4 plus or minus the square root of 2 over 2 plus 4, like that. And so that just makes this negative 4, and instead of plus or minus, it's technically minus or plus the square root of 2 over 2 plus 4. It's kind of a yucky way of writing it, but that would be what you'd end up with right there for y. And you could get a common denominator to add those together. You could certainly go ahead and find decimal approximations for those. Okay, so when we do that, and I don't know if I'm going to run out of room here, and I hate to start a problem and not kind of finish it out, so I think I'm going to do that. Be comfortable in knowing I am not going to give you a problem this messy at all, not even remotely close to this on the exam, just so you know, or on the final exam, I should say that. Whoops. Let's see. Go back. I guess I didn't copy what I was trying to copy here. So let me try to do that one more time. We're trying to find y, so I'm going to copy this onto the next page. Here we go. Well, all right, let's try this one more time. Don't want to waste too much of your time here. There we go. There we go. I don't know what I was doing wrong there. So here's our y value right here. And so you get y equals negative 4 minus or plus the square root of 2 over 2 plus, and this would be 8 over 2 right here. And so we would get y equals 8, since they have a common denominator, minus 4. And I'm going to stop writing minus or plus. I'm going to write plus or minus because it just looks nicer that way, over 2. And so you get y to be 4 plus or minus the square root of 2 over 2. And so notice that those are actually the same values. And so you end up with 4 solutions here, I'm sorry, 2 solutions here. So, and let's go ahead and look at the graphs here and see if these agree. So you're getting when I substituted those 2 x values in, I got those 2 y values. And, I was probably not being careful enough about which x value gave you which y value. And I should have maybe been a little bit more careful on that. But we're going to look at the graph and straighten this out. So remember that we've got that x is about 2.7 and x is about 1.3. So if we look at the graph here, let's see if we're getting this right graph here. Now remember that these 2 equations, you have x plus y equals 4. So let's look at x plus y equals 4. That's a line where the 2 intercepts are at 0, 4, and 4, 0. So here's my line right here. I'm going to try to be careful to sketch one that's pretty accurate right there. And then in the other graph is x squared plus y squared equals 9, which is a circle with a radius of 3. Well, I need to put that in a different color probably. So a radius of 3 means I have a circle that looks something like this. And I'm just freehanding this, and so that's why this is not entirely accurate. I could use my graphing app to have a better picture of this, but at least we'll get some feel for whether we are right or not here. And notice I'm getting 2 points of intersection right here. And remember what we were looking at in the previous problem is that we are getting intersection points at about x equals 2.7 and about x equals 1.3. And notice that exactly works out right. This one looks to be about at 2.7. It's actually 2.7, 1.3. And this one appears to be at 1.3, and that's actually 1.3, 2.7. Those are the approximations. So you didn't need to do that graphically, certainly, but I wanted to kind of go ahead and finish the problem out like that. All right, so that was a problem where we used substitution to solve the system. So let's look at some other equations. So this is problem number 8, where we have y equals x, and x squared plus y squared equals 9. All right, so this equation, we're going to also use substitution to solve this equation, this system. The first graph is a line, and the second graph is a circle. In fact, it's the same circle we had in the last problem. And notice the first equation in this case is already solved for y, so that's nice. You have y equals x, and so I can substitute into the other equation right now. And in place of y, I could simply write x, because the first equation is saying that y and x are got to be equal to each other. So when I substitute, I get x squared plus x squared equals 9. And so you get 2x squared equals 9. And so this is x squared equals 9 halves. Take the square root of both sides of the equation, and you get plus or minus 3 over the square root of 2. And so that would be our x values. And then I could use my equation y equals x. So if you have x equals positive 3 over the square root of 2, and you've got the equation y equals x, then what is y got to be? Well, y's got to be positive 3 over the square root of 2 also. And if x is negative 3 over the square root of 2, and you use the equation y equals x, you get y has got to be negative 3 over the square root of 2. And so our solutions here, I didn't go to the graph in this case, are going to be at 3 over the square root of 2, 3 over the square root of 2, and negative 3 over the square root of 2, negative 3 over the square root of 2, like that. Those would be the solutions to that system. All right, so let's look at some other examples here. We're going to go on next to problem number, let's see, let's look at problem number 24. So 24, we have x squared plus y squared equals 9. Again, our circle, same circle we've seen in the last couple of problems. So this graph is a circle. And then we have the equation y equals 3 minus x squared. Now, in this case, both equations in the system are nonlinear. This graph, remember, is a parabola. And in fact, even from earlier in the semester, we would have seen that that's a parabola that's reflected downward. Right? We could rewrite this equation as negative x squared plus 3, and we know that that parabola is actually reflected around the x-axis, right? So it's opening downward, and it's been shifted up 3 units. So it's actually one that we would have graphed earlier in the semester. So you could actually get a good idea of how many points of intersection there's going to be to this system. This is actually not a hard one to graph. Now that we've done a little bit with circles, we know that that circle has got a radius of 3. So here's my circle of radius 3, like that. And then the parabola is opening down, and it's been reflected, and it's been shifted up 3 units. So you have this vertex up here at 0, 3. And then it's been reflected downwards. So the graph is opening like this. And then let's see, we could even plot some points at x equals 2. This graph's at negative 1. Negative 2 would be at negative 1. So you get this parabola that looks like this. And so how many points of intersection does it look like we're going to have? It certainly looks like we've got 3 points of intersection. So from the graph, it appears we should have 3 solutions, right? Because there's 3 points of intersection. And one of them we can read from the graph. One of them looks like it's going to be the point 0.03. All right, so we're going to use substitution to solve this system. So let me write the system down again. So you have x squared plus y squared equals 9, and you have y equals 3 minus x squared. Now notice that this second equation is already solved for y. So that's good. So we can substitute into the other equation. Now when we substitute into the other equation, what I want you to notice is what happens here. So let's see. So if we substitute into the other equation, we have x squared plus y squared equals 9, but in place of y squared, we put 3 minus x squared. Now notice this, when you square this is going to create a problem, and so this may ask us, or maybe indicate to us that maybe we could look for a different method. When you square 3 minus x squared, you get 9 minus 6x squared plus x to the 4th equals 9, like that. And so notice you get an x to the 4th equation, in a term in there. We get x to the 4th, and then minus 5x squared, like that. And then notice the 9's actually cancel out, right? We can subtract 9 from both sides, and that's gone. And so this actually ends up not being as bad as it was going to look originally. We got negative 5x squared when we added the x squared terms together. We have an x to the 4th term. And what saves us here is that we can factor this pretty easily. I can factor out an x squared, and I'm left with x squared minus 5. And so I get x squared equals 0 and x squared minus 5 equals 0. So that gives me x equals 0, which agrees with my graph. And then I get x squared equals 5, or x equals plus or minus the square root of 5. Square root of 5 is just a little bit bigger than 2, and if you look at the graph, that also agrees with the graph. And so we're getting what appears to be a good way to deal with this. All right, so then use the equation, so now find y. So I use the equation y equals 3 minus x squared, and when x is 0, certainly you get y equals 3 minus 0 squared, you get y equals 0. You get y equals 3. And so that's my intersection point 0,3, which we found on the graph. Now when x is positive square root of 5, you get y equals 3 minus square root of 5 squared right there. And so you get y equals 3 minus 5, and y is equal to negative 2. And so that gives me the point square root of 5, negative 2, which agrees pretty well with the graph there. And then you have x equals negative square root of 5, and notice this is going to be exactly the same because you're squaring it, and you're going to get negative square root of 5, negative 2 for the point of intersection. So those are my 3 points of intersection right there. All right, now we could have done this problem a different way. We could have used elimination on this system. So let's do that and look at elimination. So this was the problem number 24. So we're going to do this problem again, but we're going to use substitution on this elimination instead. Now the reason why I can use elimination is this: there are like terms between these two equations. So since there are like terms, elimination may work. Now, if you look back at the other systems that I looked at, that's that problem. But if you look at number 8, for example, here, there were no like terms in this system. There's no terms in both equations that were like terms. And so there's no way to eliminate a variable directly. So that's why we had to use substitution. Same with this system right here. No like terms in this system. Pretty much had to use substitution to solve this system. But this problem has like terms because it has x squares in both equations. And so what I'm going to do is I'm going to line up the like terms. And so I add x squared on the second equation, so I get x squared plus y equals 3. So you line up the like terms. So that's what I did. And now you see if you can eliminate one of the like terms. And so, the like terms. So if I take the second equation and I multiply by -1, notice what happens here is that the like terms now have opposite coefficients. One is a positive x squared and the other one's a negative x squared. And so I can, in fact, eliminate the like terms. And when I do that, notice, now be careful, the y's are not like terms. So when I add these equations together, the x squares drop out, but the y's don't drop out. You just get y squared minus y equals 6. And notice you have just one variable. That's the key here, is when you end up with just one variable, it means elimination is going to work. And so I solve this quadratic. Now this ends up being relatively straightforward because this is factorable. And you end up with y minus 3 times y plus 2 equals 0. And so you end up with y equals 3 and y equals -2. And notice that's going to allow you to solve the system, right? When y is 3, you could use either equation here to solve. I'm going to go ahead and use the first equation. So you have x squared plus y squared equals 9. So that gives you x squared plus 3 squared equals 9. And notice what happens. You get x squared plus 9 equals 9. X squared is equal to 0. X is just 0. And that agrees with what we've already seen, that you get 0, 3 is the solution. And then when y is -2, then you get x squared plus, again, x squared plus y squared equals 9. You have x squared plus -2 squared equals 9. So that's x squared plus 4 equals 9, or x squared equals 5, x equals plus or minus the square root of 5. And so that gives us the other 2 points of intersection we got, plus or minus the square root of 5, -2. This actually might be a little bit easier, right, to have used elimination to solve this system. So, so elimination might work when you've got a nonlinear system. You have to look to see if you have like terms between the two equations. So let's look at problem number 12. Number 12, you have x squared plus y squared equals 25. That's a circle based on what we've talked about with this centered at 0, 0 at the radius of 5. And then you have x squared minus y squared equals 1. And when it's subtraction, when you have two squared terms and it's subtraction, remember this is a hyperbola. All right, so you have a circle and a hyperbola, and they could intersect it at as many as 4 different places. And notice there are like terms between the equations. And when that happens, you should at least try elimination and see if you can eliminate one of the variables. And notice this works out really well in this problem because notice that I can add the two equations together just like they are, and I've got like terms lined up. Remember, you have to do that. So like terms are lined up, right, in the same columns. And because they're lined up, if I add them together, notice what happens is that the y's do drop out. You end up with x squared plus x squared is 2x squared, but the y's already have coefficients that are opposites. So that those go away, which is great, and you just have 2x squared equals 26. And so notice we eliminated y in this equation. And then you divide by 2 and you get x squared equals 13. And then take the square root and you get plus or minus the square root of 13. Now, okay, so you've got the x value. Now find y, and it doesn't matter which equation I try. So if I use x squared plus y squared equals 25, and I use x equals positive square root of 13, then you get the square root of 13 squared plus y squared equals 25. That's 13 plus y squared equals 25. So you get y squared equals 12. And y is plus or minus the square root of 12 when you take the square root of both sides, which is plus or minus 2 times the square root of 3. And so notice what that gives you is it gives you the square root of 13 and then plus or minus 2 square root of 3 as 2 points of intersection. If you use negative square root of 13, all the arithmetic is identical, and so you end up with negative square root of 13 plus or minus 2 square root of 3 also. And so notice you get 4 points of intersection, 4 solutions to the system. And that agrees with what we thought about as far as the graphs in this case. So you end up with 4 points of intersection here. So the moral to the story here is that if you see like terms between the two equations, then frequently you can use elimination to solve the system. Okay, so let's look at problem number 28. In 28, we might try to use both methods on this one and see which one we think might be the better method. So you have negative x squared plus y equals 2 is one of the equations. This is a parabola because one of the variables is squared but not the other one. And then you have negative 4x plus y equals negative 1, and that's a line. So we could have as many as 2 points of intersection between a parabola and a line. All right, so let's use substitution to solve this, and then right alongside of it, we're going to use elimination to solve it. And let's see if one method is better than the other one in this case. Now with substitution, I solve one equation for either variable, right? So you solve one equation for a variable. And so this would be easy enough to take the second equation, so that would be negative 4x plus y equals negative 1, and solve for y. So solve for y right here. Remember, that just means getting y by itself. And so you get y equals, just add 4x, and you get y equals 4x minus 1. So now what do? You substitute into the other equation. So I'm going to write the other equation down again. You have negative x squared plus y equals 2. But in place of y, you substitute 4x minus 1, right? Here's where I've solved for y. I'm going to substitute that in place of y right there. So this is negative x squared plus y. So this would be plus 4x minus 1. And then that would be equal to 2. And notice this is an equation that has just one variable in it. And so I should be able to solve this system using substitution. All right, so I have a quadratic equation. I get negative x squared plus 4x, and I subtract 2, and I get minus 3 right there equals 0. And then what I would do there, since that's a negative x squared, is I'd multiply everything by negative 1 to make it easier to factor. And I have x squared minus 4x plus 3 equals 0. And sure enough, that's an easy factoring problem. Finally, we get a problem that kind of works out nicely. So you have x minus 3 times x minus 1 equals 0. And so that gives you two solutions, x equals 3 and x equals 1. And now find y. And so I'm going to use the equation y equals 4x minus 1. And so that when x is 3, I get y equals 4 times 3 minus 1, or y equals 11. And that's when x is 3. And when x is 1, I get y equals 4 times 1 minus 1, which is y equals 3. And so I get 2 points of intersection here, which agrees with what we thought about with the graph. I get the 2 points of intersection to be 3, 11 and 1, 3. And those are the solutions to the system. Those are the 2 places, the 2 points where these 2 graphs intersect each other. All right, so this was using substitution. Now let's use elimination, because there are like terms between the 2 equations. And so let's see if we can use elimination to solve this system, and let's see which method works out better. So I have negative x squared plus y equals 2. And remember, you need to line up the like terms. Now, the only like terms in the 2 equations are the y's. And they are lined up, right? So and I'm going to write that off to the side here. Line up like terms, but they're already lined up. Now I need to be able to add these 2 equations together so that the like terms drop out, but they won't if, in this case, remember the coefficients have to be opposites of each other. And so I take the second equation and I'll multiply by -1. And when I do that, I get negative x squared plus y equals 2. That's my first equation. And the second equation is positive 4x minus y equals 1. And now the like terms are lined up and they have coefficients that are opposite. So when I add these, they drop out. Now the x's are not like terms, and so I cannot add those together. And so that just comes down as negative x squared plus 4x. Y and negative y is 0. So the y's are gone, equals 3. And so now you've got this quadratic. You subtract 3 from both sides, and notice now you get exactly the same equation that I got a second ago using elimination. So see other method here. You're certainly going to get this to work out the same from here. And so in this case, when you see like terms, a lot of times you can use both substitution and elimination. So really either way, in this case would have been fine. It's really kind of what's your preference in that case. And so that's, I would have, in this case, probably have picked elimination. I typically pick elimination when I can to solve a system like this. All right, so now next time we are going to go to 3 equations in 3 unknowns, but we are going to look only at linear systems, not going to look at nonlinear systems. And we're going to use what's called an augmented matrix to solve this system using an augmented matrix. All right, so now the homework assignment for that section, I'm actually going to give you a separate sheet. There's no WebAssign homework there, but I'm going to give you my own homework sheet for that. It's not going to be due for a grade, but it is going to be something that you're going to want to look at. And the take-home problem on the final exam, remember, and I mentioned that earlier in the lecture today, the take-home problem on the final exam will come from this lecture, right? That's what this lecture is going to be about. And it's going to be a 5-point problem on the final exam. And when I say it's a take-home problem, I'm going to give it to you ahead of time, a few days ahead of time, and that's a problem that you will turn in to me by email as you're taking the final exam, right? And that will be 5 points of that final. So that when you hit that problem on the final exam, you won't have to do it, right? Because you will have already turned it into me. So the textbook homework on this section we just covered on nonlinear systems is on page 611, and I would look at, on that page, problem 7, well, problem 7 and 9 and 11 and 17 and 19. And then finally 25, 27, and 29 and 31. Okay, so give those problems a try. Those would be good practice problems. There will be a nonlinear system on your final exam, so this is good practice for the final exam. And there is some web-assigned homework on nonlinear systems also. So you have a great day. Please stop by my online office for help. I'll be happy to help you out. I have office hours, remember, tonight, Monday night, Tuesday night, and then Sunday night. Have a wonderful Thanksgiving. Have a safe Thanksgiving. Hopefully you'll get to see some family over the week. And I will talk to you again soon. Thank you.